So today we're going to look at hands-on MLOps pipeline, which was built on Fly. A little bit of introduction about me. So this is me. I'm excited about anything regarding AI, anything related to drone, everything that flies, and any combined subset of all of these two things. You can reach out to me on LinkedIn directly. I also write blogs couple of times. I started this company, Fly, as an idea straight out of college. And before college, I had worked in a couple of really demanding internships. So it started off as a platform which could make it easier to build large scale, heavy processing machine learning pipelines. Um, you can follow Fly MLOps page on LinkedIn, and also here is our website. So over to the topic for the day. We are looking at road quality and predicting road quality using AI. So what is the intent behind this pipeline? So India has the second largest network of roads, which is around 62 lakh roads, which is only set to increase in the next 10 years. Maintaining roads is itself an expensive affair because each year you have got heavy monsoon rains in most of India, and every summer you have got a lot of heat, which kind of tends to play with the roads quality every year. So every year they have to be surveyed, they have to be mapped, and the damage has to be filled in. So it is a pretty extensive affair requiring a huge amount of manpower, money, time, and resources. And that is why we thought that it was a very nice, interesting problem to solve, and something which, if we created a POC pipeline right now, it could be implemented at scale by somebody in some years into the future. So that is a that is the rationale behind choosing this pipeline as a POC for our platform. So basically, let's start with the data. So I like to give you the scenario first, behind the collection of this data set. So how this data set was collected by the organization that made this data set. So consider there's a car. The car is an electric car. It's not a engine driven car, and it is driving along a road. Now it has got the GPS coordinates. It has got the speed, the acceleration of the car, the elevation the car is moving along. All of these paradigms are recorded by the instrumentations on board the car. Next, we have got in each of the left and the right suspensions of the car a set of gyroscopes. Now gyroscopes is a gyroscope is an accelerometer, so that accelerometer measures the vibrations in the suspensions of that car. Now you can understand where we are going. So you have got the GPS data, you have got the uh, uh, you have got the uh, uh, this thing, um, uh, elevation, you have got all these sorts of data sets, and then you have got the gyroscope data along with which is mapped to the timestamp. So say the car rode around for 2 hours, then the timestamp basis records are set here. So you've got three subsets of the main data set. So you have got three separate data sets, I would say. So the first data set is all of these external phenomenon or external factors, which is the speed, the GPS coordinate, the elevation. Since it's an electric car, we also have the battery status of that car. Your second data set is just the gyroscope reading. So gyroscope readings in itself are a complex collection phenomenon. You have got the X, Y, Z axis, and you have got two gyroscopes, one on the left side, one on the right side. So it is these combined readings and the temperature reading. So the temperature, because of the vibration, the temperature of the gyroscope is either increases, or when it slows down, it decreases. So these are the temperature readings, and this is the second data set which we are going to be dealing with. So now you must have had a quick overview of what kind of data we are dealing with. So we have a car, we have got all the location, the GPS, this, that, the external factors, the basically the geolocation of the car. The second data set is the internal factors or the suspension data from that car. And finally, we have got the labels data set. So In this data set particularly, which was collected somewhere in Netherlands by European University, um, this data set has got a three-way classification of the roads. So they have classified the road tracks as either asphalted road, which is your regular road, uh, either cement or tar, and then you have got a cobblestone road, which is kind of stones laid into the road, and you have got a dirt track, which is nothing at all. So this is the labels against the timestamp, wherein it is a one hot encoded data set of binary characteristics. So it's either 1 or 0. And this data set is what we convert into a human readable data set so that we can make sense of it. So these were the three data sets that we have. Now let's go to the experimentation lab. Now we are in the experimentation lab, which is a notebook, uh, which is a component within Fly, which is part of Fly MLOps tool. Now let us look. Now this was the first data set that I had shown you, the external parameters data set. And what we have done here is eliminate a couple of the columns, format the date time, and get the final process data set. Now in the second part, we have got this. So this is the third one. So I'll move to the second one. So in the second part, we have got this rather large data set of the gyroscope readings and temperatures. Now, the gyroscope readings are a complex phenomenon which, due to lack of time, I cannot explain here fully. But let's assume that it's simply the x, y, z coordinates of the gyroscope, and it is taken as a vector, so as a complex number. So the magnitude and the angle at which that movement happens of the acceleration of the accelerometer, that is what it is split into. So the magnitude and the angle, and that into that into two for both the left and the right gyroscopes. This is basically the summation of the second data set, and that is what we have compiled here um, in the experimentation lab. And then the third data set, which is the one hot encoded data set, which is against the timestamp again, which we combine to form the um, human readable data set. So in terms of the road condition and bumps means that whether there are any aberrations or not in that road quality. So even a paved road is never going to be always smooth. So there are going to be bumps at from time to time. And this is the third data set. So this is the data pre-processing which we have done on in the experimentation lab. And so this is when we combine all of these three data sets. So you have got the GPS coordinates, latitude, longitude, the timestamp, the speed of that car, the acceleration of the car, then the readings of the gyroscope, and the road condition parameters. This is the combined data set which we arrive at using different pandas functions, numpy functions, so on and so forth inside of our experimentation lab. Now, once we are done with this, and this is the combined data. So I'll go over this again quickly. You have got your first data set, which is timestamp versus the speed, GPS coordinates, elevation, battery status, so on and so forth. You have got your second data set, which is the gyroscope readings and the temperature readings at the suspension level and the dashboard level, which I'll explain in a bit. And the third data set, which is the one hot encoded data set of the road quality labels that is converted to a human readable data set. And all of these three data sets, one, two, three, we have combined into one combined data set. Now look at the number of records. It is 1,44,035 records. And this is the nature of this combined data set. Now all of this comes under the uh, domain of data cleaning or data pre-processing. And this is the data pre-processing stage, which is just one stage of our entire pipeline. Now we move to the next stage, which is feeding this pre-processed data into the models. And I'm again going to switch my tab here. So this was our notebook from the data cleaning stage, dataset 1, dataset 2, and dataset 3. And then finally, we get the combined data set. Now, what we have done for simplicity is, because there are a lot of more stages which are going to come in the pipeline, we have combined this entire notebook according to the two titles which you can see, which is GPS pre-processing block and the normal pre-processing block. So all of this entire code is what we have combined into this notebook, which I'm again going to show you. So that one Jupyter notebook, since the data cleaning part was only a few stages of the entire pipeline, is what we have compiled into two blocks. So the one which I was showing before was the RQA1 notebook, and now we have converted it into just two blocks, the entire notebook. And this is your block one, which is your GPS pre-processing. Your block two is your normal pre-processing. Now you can import uh, on Fly MLOps tool, you can import Jupyter notebooks directly, and that is what we are going to do. So just confirm if I am on the Fly MLOps screen.
Yeah, yeah, yes.
Or so here you can import Python files, you can import blocks which are Fly entities, but we'll talk about that later. But I'm going to import a Jupyter notebook directly. So the Jupyter notebook which we had compiled, I'm going to import it directly. And there you go. These are your blocks. And you have your code within them. So this is your GPS pre-processing block, and this is your pre-processing block. Now, Fly, in essence, without going into any complex details, is the abstraction between your code and what enables you to run that code. Now, for such a massive pipeline, it can't be run on even the highest configuration PC or laptop that there is. It is very hard to run, or it takes a longer time to run on your Office servers also. So 64 GB RAM servers also take a long time. So in the backend, we have a cloud engine running on top of our architecture called as Kubernetes, which is used to empower this entire pipeline. And Fly as a tool abstracts your effort of creating or deploying that infrastructure. So any cloud infrastructure, AWS, GCP, this, that. Instead of that, Fly comes in between as a middle layer where you can drag and drop your things and get started. So because of that, because of not being on your PC and being outside, you have to import the files that you need for this processing into Fly. So that is the function of the data import or data input block, which I have shown here. And I'm just going to connect and show you one or two examples, and then we can move on to the next process. So this is your data input block for the GPS data, and I'm just inputting the credentials for my Google Cloud Storage bucket. Okay, there we are. So I'll be selecting the files which I want to bring into Fly here in this data input block. So I'll select, let us say, any of, these three files. I'll give them or transport them to the next block. Now, the one thing about the architecture which we use, Kubernetes, is that between any two blocks, on Kubernetes, you have to configure it. You have to tell it that, okay, these are the files that I want transferred from one block to another. So we've got three basic kinds of blocks, which are the data import, data input blocks, which bring in the data files into Fly. We've got the function blocks, which, as you can see, run most of the complex pre-processing or complex codes. And then we've got the visualizer blocks, which you can use to generate visualizations then and there itself in situ. So we take a couple of visualization blocks and we connect them. Let's say label them and put in the code. So visualization blocks also have some kind of code in them, which is mainly the code that is used in the standard Python visualization libraries. So matplotlib, Seaborn, etc., etc. So I'm just going to put in some code into these things, and then I'm going to configure both the function block and the visualization blocks. So this is just a sample of how a pipeline is made. Of course, this operation takes a lot more longer. So you have got this common package management here, where you can select packages required for, say, all of your pipelines, and you can individually manage your packages, say from here. So you can select packages for, um, you can select the container base image, which is kind of the container image for your Docker container, which each of these blocks is in the background. And finally, you select the package management and put in the code. And I'm just going to go to the final ready version of this pipeline without taking too much time. Um, so this is the final version of this pipeline. This is how it looks like. Keep in mind that the real uh, pipeline will be much more complex with much more number of blocks. But for the purpose of this demo, what we have done is we have taken a short abridged version and cut out a few branches which were not necessary for this demo per se. Now, as you can see, it's got three different branches, and on the left side we have got the GPS data, which is incoming, and um, you have this pre-processing stage, which I just explained in the experimentation lab, brought in, and then you have got these visualizations. So each of these visualizations actually um, gives you some insights on what this data entails. Now, this pipeline as a whole takes around 15 to 20 minutes to run because it is a pretty large pipeline. But I've already run it for you, and here you can see some of the results. So this is elevation plot of that car. So you can see it was at around an elevation of 1,000 meters, which is pretty much in hilly areas. Then it went down, and then it again comes up. The elevation plot versus time. You've got the GPS coordinates plotted of that car, so you can see the path that it took. And since it is an electric car, it also has the battery level of that car. It shows the battery level versus the timestamp. Now, the reason to show this EDA is I want to elucidate on how much easy it becomes when you create your entire pipeline, however complex it might be, on a flowchart type drag and droppable interface. This is where you can get a hang of the data, what goes where and what is happening. The second part, which I had shown you in the experimentation lab, was that we had compiled all the three data sets into one. So this is that block, which is it doing it one in one go, one shot, and then it is giving us the next stages of the pipeline. Before going to the part where the ML models of the pipeline are, I just want to show you a couple of things from the right side of the pipeline, where you have got the data set of the gyroscopes and the temperatures, um, which is exactly this data set, and you've got some analysis done on that. So the gyroscopes that are attached to the suspension have temperature sensors also. I mean, there are temperature sensors also along with those gyroscopes. So there is one temperature above the suspension, one below the suspension, and there's one temperature sensor on the dashboard of that car. Keep in mind, this is an electric car, so electric cars don't have any heating due to the engine as such. Now, this plot maybe for a layman like us will not tell us much, but for advanced mechanic or let's say a thermodynamics engineer or someone, it is very meaningful and it gives a lot of insights when you have got a car that is going on different kinds of roads. And then the temperature that is mapped for the suspension, maybe it can predict how fast the wear and tear of that suspension is going to be, how much does the kind of road affects, and how many cycles does a car, say in a rural area where the roads are not so good, uh, need to have its suspension changed versus the car where in a urban area where the roads are good needs to have its suspensions changed. So the wear and tear and all that study, this graph is for those researchers. We have one more graph here which is very useful for data scientists, and that is the heat map. So since you have got now, when you have compiled the data set, you have got a sorry, for the heat map data set, you have got around 32 columns. Now 32 columns are a pain when any machine learning engineer looks at it, especially if you have to give it to an ensemble model like say a random forest or a XGBoost. You try to reduce the number of columns that there is by finding the correlation between different columns and eliminating the columns which have a positive correlation. So the darker cells that you see, and this is not a very good plot because it's plotted for a large number of variables, almost 20 variables. But if you can plot it batch wise, then you can have a large number of these columns which have a higher correlation. Say, let us just see mag X dashboard, mag Y dashboard. You can directly eliminate these, and then from say 32 columns, you can condense the data set down to 16 columns, which makes it very easy for your model and makes the model also much more accurate. So this is the use of the heat map. So now we have covered pretty much the stages where you have done some EDA, you have done some exploration of the data, and you have mapped the correlation, eliminated a couple of columns, and finally you are at the stage where you want to now train and test your model. So in the models, we have got unsupervised learning and a supervised learning model. So in the unsupervised learning, we have used a k-means clustering model, which directly gives you, um, say, n number of clusters. Say if you input three, it will give you three number of clusters formed out of the data using some kind of calculation of the vector distances between these cluster plots. Similarly, we have got supervised learning model, which is a LSTM neural network model. So LSTM is a long short-term memory network model, which means that it takes in accord the previous bias or the previous, say, record of what it has learned also into account with a certain amount of weightage, and that is why it is called a long short-term memory neural network. So the way neural networks work is a pretty complex topic, and it's not for today. But in short, we have used LSTM because here we are predicting the nature of the roads, and the nature of the road doesn't change randomly, doesn't change abruptly. So the previous weightage or the weight of the previous value, say at X timestamp, the road was a dirt road. Then at X plus zero point 0.5 seconds or X plus 1 second timestamp, the road is still going to be pretty much a dirt road. And the transition between a dirt road and an asphalted road happens. Um, I mean, it does happen in a certain manner, but most of the times, whatever the previous value of the road was, is what is the next value or the type of the road. So, how have we used these two models in this pipeline? Let us go back to the pipeline. So, here we are back to our pipeline. And let's look at the clustering model first. So once we have completed the experimentation lab part, which is the data cleaning, the data pre-processing stuff, you don't go back into the Jupyter mode because it's much easier to work on a flowchart based interface. Now what do we do is we put in the code directly for the k-means clustering model. And here, as you can see, we have put in the scikit-learn k-means cluster. We use the scikit-learn k-means cluster library, and we have to import that library first. Scikit-learn, we have imported it here in the packages to install inside of this container, and then we have directly used it. Now, since this is the model, let us look at the insights that the model gives us. So first one, of course, since it's an unsupervised clustering algorithm, we look at the cluster plot. So this is the gyro reading on the suspension. So the reading of the gyroscope on the suspension of that car versus the speed plotted for that car. Now it's pretty common sense to say that okay, the speed of the car will be high and gyroscope reading will be low, means that the road is a well tarred or a smooth road, asphalted road. And that's what you see on the right side. But look at the difference and kind of the very easy to see border line that you get. Look at the cursor which I'm dragging. between the cobblestone roads and the dirt roads. So this is a European setting. So cobblestones are these big kind of stones which are put into mostly into walkways and not into dirt roads. Sorry, not into roads for cars, but you have got these cobblestone roads which are much more tougher for the car, which are giving a much higher gyroscope reading, and the driver is having to drive much slower on the cobblestone road generally as compared to the dirt road, which is quite a bit smoother. So that is one nuance you can see, and you can derive from these plots and the k-means clustering model. um, Second one is, of course, a direct plot between the acceleration of the car. Now keep in mind, this is the car's acceleration and not the gyroscope reading, the car itself, the vehicle, versus the timestamp. So this is for the entire journey. And as you can see that the acceleration plot is so haphazard, and it is just, its car is revving up, it's revving down, it's revving up for whenever the road is bad, whereas whenever the road is well tarred, it is good, the acceleration reading immediately drops down. This is obvious because the asphalted road does not need you to slow down, speed up, slow down, speed up constantly. You can maintain pretty much a constant speed. And the impact of this, I mean, for say fuel savings or engine cycles, this that tire wear and tear, can be from this graph and from this data directly calculated by the experts in that field. So this is the second graph, and third one is a heat map that shows kind of the correlations between the different factors and the type of the road. So you have got your gyroscope reading, you have got your acceleration, you have got your speed, and you have got the quality of the road versus the type of the road. So whether it's asphalt, whether it is dirt, or whether it is a cobblestone road. And this heat map allows you to make certain decisions for the next flow that you can implement. So this was the unsupervised learning part of the model or the pipeline. Now we are going to have a quick look at the supervised learning part of the pipeline. And this is the LSTM model. LSTM is, like I said, it's a neural network. So we use the TensorFlow library. We use a TensorFlow sequential library. And here you can set in different parameters um, for the LSTM neural network. And then you fit the model or you train the model on the data, and then you test it. So the way machine learning works is you divide your existing data set into a training and a testing data set. So you have got a training data set, say 80% of the data, which you are going to give it to the model. And in layman's terms, just the way a kid or a baby learns something, wherein if it has to learn a pronunciation, then it will kind of pronounce that word in the wrong way 100 times before it gets it right. Similarly, in ML, it gets the 10 times, 100 times amount of the data for that one single sample to be able to next time predict new incoming data correctly. And this is called the learning stage of the model. And then you have the validation stage where you check using the remaining 20% of the data that you had kept aside, whether the model has learned in the right way how to draw the conclusion between whatever you are giving it to, whether to classify or as a to quantify as a regression, whatever it is. So now in this LSTM model, what you have is a sequential network, and it's got a certain learning rate. It's got a certain these are now different technical parameters of the model itself, which is the dropout, etc., etc., and the activation function. Finally, you can visually see and plot the accuracy of this um, against the epochs or the learning cycles of this particular class. So the way neural networks work, so LSTM is in a sense a recurrent neural network. A recurrent neural network is something that will redo that learning stage again and again and again with certain variations and check if it is right. And so here you can see that, and that each redoing is called a epoch. So here you can see that this model has been run for 25 epochs, which is quite large, by the way. And by the, say, the second or third epoch, it has already achieved the saturation of accuracy, which is somewhere around 84%. um, so this is the 84% is the saturation accuracy for the training data set, whereas for the validation set, the 20% that I told you about, it's somewhere around 82%. So um, for each epoch, the model is supposed to improve, and it does go on improve in the early stages, where it goes on learning more and more, and improving the function with which it predicts, say, the road quality using these different input parameters: the temperature, the accelerometer reading, so on and so forth. And at one certain point, it uh, basically stops. So now, one easy way of making a better model or optimizing your model is to do hyperparameter tuning. So in this block, the, say, the dropout, the current dropout, um, uh, the learning rate, all of these are hyper parameters, which means that you have to, these are the input functions, or the input parameters, the control parameters for these functions, which when you change, you are going to get different results. So instead of hard coding them, what we allow users to do is to set the pipeline control parameters here. So you set this n clusters was for the k means. So you set the number of clusters, and it you can um, so you I just show you how we add a new parameter. Let us say we add a new parameter, param1. We select the data type, whichever it is. So we'll select float, and we select which block it should go to. So now remember, this is a whole pipeline, but since you want to take runs again, improve, you should not have to go into the code which you have written again and modify it manually. So instead of that, what we have done is we have given the control parameters to be abstracted, to be taken out of the pipeline. So you can choose which block this control parameter goes to, and then using that control parameter, you can directly take that value from the pipeline control parameters. And the way this works is, uh, so you have got these four control parameters here. So you've got, for k-means, you have got the number of clusters, which in our case is 3. For LSTM, you have got the number of epochs, which, as you saw in the graph, it was 25. You have got the recurrent dropout rate, and the units, which are all different hyperparameters. And when you have configured this, you have told Fly basically that these are the parameters that I want to abstract, I want to take out of the pipeline. The rest of those, whichever what are there in the code, you can use. And then when you click on run, this pipeline has already been run for you to save time, but let us do that for the heck of it. So when you click on run, it will ask you what values you want to give it for this particular run. So let's say number of clusters is 3, the epochs is again 21, recurrent rate is zero point 0.3, dropout rate is zero point 0.2, and units is 80. And now I have given these things, these hyperparameters. It will go for a run again. So of course, each run takes around 20 minutes. But 20 minutes, mind you, for this kind of infrastructure is a pretty small time. So this pipeline, this particular, the exact code will not run on your PC or your laptop, even if it's the best laptop that there is. It takes a couple of, at least 1.5 hour to 2 hours to run on, say, a server, a 64 GB RAM server configured, or say a single compute instance of any cloud platform. But on Fly, it barely takes 20 minutes to run. So I'll pause the run now. I'll stop the run because we don't have that much time. Um, and I'll just retrieve. So Fly allows you to retrieve some of the past runs. You can save a version of the pipeline that you have created also, at some point of time. So this is like caching, and you can retrieve past runs which were say given for different hyperparameters. Yeah. So as that is the entire pipeline from start to end, where you ingest the data, you do the data pre-processing, cleaning stages in the experimentation lab, then you go on to fly the dashboard platform, and you um, take the EDA graphs, you take some cognizance from that, do the models, whichever. I mean, you can have n number of models. We've had one pipeline where we had 4 models running concurrently, um, in within the same pipeline, and we took whichever one gave us the best or the more optimum kind of results. And finally you have got your ready package model, which then you can extract as say pickle file or a joblib file, and you can plug it in whichever into whichever inference service that you would want to use to serve that model. So the end goal of fly is to give you a servable model with all the um, um, fine tunings, with the hyperparameter tuning done, ready to use in any end application. um, so that's it. Do follow our company page for constant updates. Those of you who have interesting topics to talk about can reach out to me directly on my LinkedIn. And also, we are a startup, so it is pretty difficult for us to release or say give out free trials to the public, so as to say. So currently we only give out demos and limited free trials to large companies or organizations which are interested in our tool. So if you want, um, if most of you viewers want to have a free trial, a go, or say a small bit of the chocolate, send us inquiries on our email address, demo@flyMLOps.com, so that we can advertise it to investors. Say, hey, we've got 3,000 inquiries, and now please give us money so we can actually give retail free trials. Um, Thanks a lot for this session, and I really enjoyed it. Um,
Yeah, before we proceed to answer your questions, I would like to request the attendees to please fill in the poll about feedback as it helps us to conduct more such sessions. Sir, should I be picking up the questions or will you pick it up? You'll
no, you
get
can pick
the
it up.
yeah, yeah,
You can pick it up totally.
yeah, yeah. So there's a doubt from Mohammed Hanini. CNA, can this Kubernetes pipeline be used with R?
Theoretically, yes, it can. Practically, we have not achieved that yet. I mean, to transcend the languages between, say, two components or two blocks.
The validation accuracy is flat across all the epochs. What can we infer from this?
Um, I would have to ask that question to one of the data scientists on my team who actually built that model. I've been thinking of asking it for quite a long time, but yes. Thanks a lot, guys.